A nanowire battery uses nanowires to increase the surface area of one or both of its electrodes. Some designs variations of the lithium-ion battery have been announced, although none are commercially available. All of the concepts replace the traditional graphite anode and could potentially improve battery performance. Silicon. Silicon is a desirable material for lithium battery anodes because it offers extremely desirable material properties. Silicon has a low discharge potential and a high theoretical charge capacity 10 times higher than that of typical graphite anodes currently used in industry. Nanowires could improve these properties by increasing the amount of available surface area in contact with the electrolyte, thereby increasing the anode's power density and allowing for faster charging and higher current delivery. However, the use of silicon anodes in batteries have been limited by the volume expansion during lithiation. Silicon swells by 400% as it intercalates lithium during charging, resulting in degradation of the material. This volume expansion occurs anisotropically, caused by crack propagation immediately following a moving lithiation front. These cracks result in pulverization and substantial capacity loss noticeable within the first few cycles. Research done at Stanford University indicates that silicon nanowires grown directly on the current collector are able to circumvent the negative effects associated with volume expansion. This geometry lends itself to several advantages. First, the nanowire diameter allows for improved accommodation of volume changes during lithiation without fracture. Second, each nanowire is attached to the current collector such that each can contribute to the overall capacity. Third, the nanowires are direct pathways for charge transport. In particle-based electrodes, charges are forced to navigate into particle contact areas. Silicon nanowires have a theoretical capacity of roughly 4,200 mAh/G⁻⁻1, which is larger than the capacity of other forms of silicon. This value indicates a significant improvement over graphite, which has a theoretical capacity of 372 mAh/G⁻⁻1. Additional research has involved depositing a carbon coating onto the silicon nanowires, which helps stabilize the material such that a stable solid electrolyte interface forms. An SEI is an inevitable byproduct of the electrochemistry that occurs in the battery. Its formation contributes to decreased capacity in the battery, since it is an electrically insulating phase. It can also dissolve and reform over multiple battery cycles. Hence, a stable SEI is preferable in order to prevent continued capacity loss as the battery is used. When carbon is coated onto silicon nanowires, capacity retention has been observed at 89% of the initial capacity after 200 cycles. This capacity retention is on par with that of graphitic anodes today. One design uses a stainless steel anode covered in silicon nanowires. Silicon stores 10 times more lithium than graphite, offering increased energy density. The large surface area increases the anode's power density, allowing for fast charging and high current delivery. The anode was invented at Stanford University in 2007. In September 2010, researchers demonstrated 250 charge cycles maintaining above 80% of initial storage capacity. However, some studies pointed out that nanowire anodes shows significant fade in energy capacity with more charge cycles caused by the volumetric expansion of nanowires during lithiation process. Researchers has proposed many solutions to remedy this problem. Published results in 2012 showed doping impurities to the nanowire anode improves the battery performance, and it is showed that phosphorus-doped nanowires achieved better performance compared with boron and undoped nanowire electrode. Researchers also demonstrated the possibility of sustaining an 85% of initial capacity after cycling over 6,000 times by replacing nominally undoped silicon anode into a double-walled silicon nanotube with silicon oxide ion permeating layer as coating. The silicon nanowire-based battery cell also provides opportunity for dimensional flexible energy source, which would also lead to the development of wearable technological device. Scientists from Rice University showed this possibility by depositing porous copper nanoshells around the silicon nanowire within a polymer matrix. This lithium polymer silicon nanowire battery has a sufficient operational full cell voltage of 3.4 V and is mechanically flexible and scalable. Commercialization was originally expected to occur in 2012, but was later deferred to 2014. A related company, Amprius, shipped a related device with silicon and other materials in 2013. Canonical announced on July 22, 2013, that its Ubuntu Edge smartphone would contain a silicon anode lithium-ion battery. In January 2015, Eagle Picker announced that it has signed an engineering agreement and a license agreement with Wand Material, a spin-out from Nanosys, to vertically integrate the production of a silicon nanowire on graphite anode called SiN-anode into new high-energy density cells and batteries, manufactured in Joplin, Mo. Germanium. An anode using germanium nanowire was claimed to have the ability to increase the energy density and cycle durability of lithium-ion batteries. Like silicon, germanium has a high theoretical capacity, expands during charging, and disintegrates after a small number of cycles. However, germanium is 400 times more effective at intercalating lithium than silicon, making it an attractive anode material. The anodes claim to retain capacities of 900 mAh per gram after 1100 cycles, even at discharge rates of 20 to 100 C. This performance was attributed to a restructuring of the nanowires that occurs within the first 100 cycles to form a mechanically robust, continuously porous network. Once formed, the restructured anode loses only 0.01% of capacity per cycle thereafter. The material forms a stable structure after these initial cycles that is capable of withstanding pulverization. In 2014, researchers at Missouri University of Science and Technology developed a simple way to produce nanowires of germanium from an aqueous solution. Transition metal oxides. Transition metal oxides, such as a Cr2O3, Fe2O3, MnO2, Co3O4 and PbO2, have many advantages as anode materials over conventional cell materials for lithium-ion battery and other battery systems. Some of them possess high theoretical energy capacity, and are naturally abundant, non-toxic and also environmental friendly. As the concept of the nanostructured battery electrode has been introduced, experimentalists start to look into the possibility of TMO-based nanowires as electrode materials. Some recent investigations into this concept are discussed in the following subsection. Lead oxide anode lead-acid battery is the oldest type of rechargeable battery cell. Even though the raw material for the cell production is fairly accessible and cheap, lead-acid battery cells have relatively small specific energy. The paste thickening effect during the operation cycle also blocks the effective flow of the electrolyte. These problems limited the potential of the cell to accomplish some energy-intensive tasks. In 2014, experimentalists successfully obtained PbO2 nanowire through simple template electrode deposition. The performance of this nanowire as anode for lead-acid battery has also been evaluated. Due to largely increased surface area, this cell was able to deliver an almost constant capacity of about 190 mAh/G-1 even after 1000 cycles. This result showed this nanostructured PbO2 as a fairly promising substitute for the normal lead-acid anode. Manganese oxide MnO2 has always been a good candidate for electrode materials due to its high energy capacity, non-toxicity and cost-effectiveness. However, lithium-ion insertion into the crystal matrix during charging, discharging cycle would cause significant volumetric expansion. To counteract this effect during operation cycle, scientists recently proposed the idea of producing a Li-enriched MnO2 nanowire with a nominal stoichiometry of Li2MnO3 as anode materials for LiB. This new proposed anode materials enable the battery cell to reach an energy capacity of 1,279 mAh-G-1 at current density of 500 mA even after 500 cycles. This performance is much higher than that of pure MnO2 anode or MnO2 nanowire anode cells. Heterostructure TMO's heterojunction of different transition metal oxides would sometimes provide the potential of a more well-rounded performance of LiBs. In 2013, researchers have successfully synthesized a branched Co3O4, Fe2O3 nanowire heterostructure using hydrothermal method. This heterojunction can be used as an alternative anode for the LiB cell. At operation, Co3O4 promotes a more efficient ionic transport, while Fe2O3 enhances the theoretical capacity of the cell by increasing the surface area. A high reversible capacity of 980 mAh-G-1 was reported. The possibility of fabrication heterogeneous ZnCO2O4 NiO nanowire arrays anode has also been explored in some studies. However, the efficiency of this material as anode is still to be evaluated.